my name is Thomas Werle. I'm the CTO of the ERNE AG, and I'm in the at the ERNE since 16 years, and started my career with education at the Fachhochschule Rosenheim as a timber engineer in 1995. So that is my background. So short words to the company. It's a family-owned company in the fourth generation, 1906 founded as a construction business, normal concrete. Then he buy a window factory, 45, and that is the beginning of the timber company in the ERNE holding today. So 1950 we realized first systems in wood, and 1965 we make a cut. So we have two companies, the concrete one and the timber one. So then 95 we developed the first room solutions for industries like containers on site. Then 2009 we installed the first our first automation with the largest multifunctional bridge we installed. It's the biggest one in Europe, 2009. Then 2014 we start up with Europe's largest gantry robot. Some of one maybe use this in 2018 for the robotic workshop, who was in the ERNE company. And 2018 also we installed our first KUKA KR 240 for prototyping and R&D. And 2019 the fourth generation coming to the company. And that's cool. So also today a family-owned company. So this is the holding today. We have three parts. We have the construction above and below ground. That is the concrete and brick part. Then we have the timber construction with ERNE AG Holzbau. We have an office in Germany, and we have a sister company that named Husner in 10 minutes from here. So he do the normal carpentry work. And then we have some real estate in the holding. To the company, to the ERNE AG Holzbau, that we have today more than 300 employees and a turnover around about 135 million Swiss franc, with different sites in Laufenburg, that's in Switzerland, and Stein, also Switzerland. Pentalas, that's in the French part of Switzerland and in Germany. And the factory area is more than 100,000 square meters. So it's very big. We have different sites with different halls, production halls. So what about the digital workflow? So we normally talk or say we are planning and do a fabrication according to the BIM methodology. Then we have a gantry robot and multifunctional bridge. We do research and development with our KUKA robot. We have a fully automatic window production line, and we had robot spraying system for the windows frame. So that is so for this we need a digital workflow. We need some information, data, to bring this in a good quality out of the hall to the site. So also we think that the individual solution is a good idea. So we are based on a material independent construction method. That means that we use a lot of materials. We have it in the holding. We have know-how in the concrete. We have know-how in glass. We have know-how in wood. Now we also have know-how in steel, so we can combine this, and this up to the quantity from one. And what we say is that the quality raise up or is guaranteed in form that we can do it with an industrial fabrication or in prefabrication. And the high degree of prefabrication reduces, we say, the complexity on site. So that means it's better, or it's like a lean process on site. So if you talk about prefabrication, short time on site and all these issues you have. or topics you have when you build a building at the end. So some projects we have done for Herzog Dömerer in Switzerland. This is Südpark 2010. It's 10 years ago. In this time between 2020 and 2010, we have done several projects. But this is, yeah, for me, it's cool. It's a different, yeah, a lot of different pieces. Yeah, it's very special at the end. And in this, yeah, in this project, we also do digital blending. You see it on the left. All the walls are digital blend and also prefabricated, not digital. We are done it by hand. You see the construction site or the building on site with the elements, and on the left you have, yeah, the installed hall with these prefabricated elements. Special, but at the end it looks like this. You see on the left the inner view, and on the right it's the edge of the building. That's not finished yet, but the inside is finished with oak, and it looks very crazy. It's very cool to do that. So, at the end we talk about digitalization. How can we handle the information or the data? And for us, we have created a roadmap for the digitalization. And at the end, we have find out that we have 5 different parts. That is digital construction. We have the digital fabrication. That is where the timber company comes or do. Then we have the digital facility management. We have the digital design. That's a parametric and all this stuff. And then we have the digital planning. And part of the digital planning, we say, is at the end BIM. So, and all these parts are connected with the big black box named digitalization in the construction or building industry. And that is the big challenge today. How can we connect all these different parts in a way that we can, yeah, exchange the data and bring this in a good form that everybody can use it at the end. So that is the big challenge today. And if you talk about timber construction, so timber construction construct with or are part of a digitalization since 1980. So that we can say today these highlighted parts are today part of the timber company or timber construction use this or can handle this. So that means the digital production, that's normal. Then we have know-how in digital planning with Lean, VDC, and BIM, and also digital construction with point clouds and digital tools on site. So why have we this know-how? So 1984, we started a very simple machine that is, it's a cutting machine, and then we have to bring in all the information directly from the paper drawing directly into numbers and type it into these machines. So, and at the end, it's a surprise what comes out of the machine. Today, you see the picture on the right. That's a picture from the ETH in Zurich. This the RFL Robotic Fabrication Lab, when we produce modules for the DFAB house, 3-dimensional with 2 robots in collaboration directly from the 3D model. So, and that is the way we have gone the last 30, maybe 40 years. So the modern timber construction produces digital with robots or CNC technology. Then we do the planning digital like this. So we have for every building a digital twin at the end to steer the machines and create all the information we need for the building site. We integrate the HVAC at the end. So if nobody can say how big are the openings or where are the HVAC components laying in the model. So we integrate this and do it by ourselves. And the next one is the reinforcement, so that we also generate the reinforcement for it's the wood concrete composite elements in this building. It's a high-rise building is 40-story high, 60-meter in the height, and it's a hybrid building between concrete and timber. So, and we coordinate trades at the end. So on the left, you see the picture from the HVAC planning. The left top is done by us, and the right down one is done by the HVAC planner. And then we combine this together to a complete model to look at the collisions and does it work, and where are the problems and challenges at the end. So that means if we talk about the high prefabrication or the steps of a high prefabrication, that means that we need more planning in the beginning of a project, and that means at the end that we have to exchange our models more and more, and that is the big challenge today. If you look back to the roadmap, and you have the big challenge that from the digital planning you go directly to the digital construction or the digital prefabrication. So, and that means at the end that we have to think in combined models. So on the right you see the normal simply parts. Everybody thinks for themselves, not together, and that is the new process that we have to think together for a project, so that we can bring in all our know-how for the project together and find out the problems, and then we can solve it together, and everybody knows from each other what is his challenge in this project, and maybe can help. So at the end, I want to bring some examples for that. That is an example that we bring it from the Hüllkörper model. That means it's like a very simple volume to the production model. So it is our design model that we get from architects or create by ourselves, and from this we extract at the end our construction model. So with rules, so the only thing we need is the dimension of the wall. We need the opening, that is also a volume. And in this, we have one or two attributes or information we need. It's like the wall or the volume have to know I am a wall, and the volume has to know which type of wall, type R, type A, B, or C, or A1 or A2. And with this information, we can create the construction model from the wall in the timber engineering. Then from this we extract for ordering the material, the timber model at the end. And when we create all these walls, we also install the electrical installation with rules. It's very simple. Every door needs at the end electrical switch or whatever, or connector, and that you have rules there, so you can implement this in the parametric way, so that is not so heavy. It's very easy to do that, and then you have all the information for the production line. So then we bring this material model into our database. So we load it up into the database, and then the database generates automatically the whole material list. You see it on the left. Then you can combine it with the supplier, and then you can send it to the supplier. So the supplier gets the list, and the supplier gets the 3D model. That is a native model, and all our suppliers can handle the native model. So it's very easy. At the end, we get back a price, and then we can compare this, and then we can order the material directly by clicking on this, Einkaufswagen, on this trolley. And at the end, all of these people who are involved in this process, from the construction man to the ordering people up to the people in the production, all have rights to see all the information directly from this database. So that means at the end, we have different positions. We have all the documents we need or get from the supplier. And at the end, we know which material belongs to which project, who is the supplier who ordered the material. And at the end, when is the delivery time or date, when comes the material into the company, so that it can be produced. produce the elements at the end. So, and the other one is the quality. So we have some quality rules. So there's it's a sheet of paper. We have to fill it out by hand. That is a rule that is given from the it's not from the government. It's given from the company who do this to check this. And at the end, all you have these delivery papers, and you bring this all to a scanner and the QR code. Scan all these documents and save it directly with the QR code into the right position on the server to the project. So it's very easy to digitalize this information at the end. So what we get back from the supplier is it's a numbered wood, a 3D model with a lot of information. You see it on these stickers, and the question is that BIM? We say it's part of BIM. It's handling information in a 3D model. That's a lot of information. It's a column in the top, or it's only a beam. How big is the column? To which project it belongs? What is the number of the column? He knows to which wall he belongs at the end. Exterior wall 105 or inner wall 046. And which project it is. So that is what we get back, and then we generate all the drawings for the production, also the CNC data. Then we go into the prefabrication with our machines. On the left you see the multifunctional bridge, on right you see the big robot, the gantry robot. And then we do some prefabrication in the production hall, prefabricate the containers or the modules, the 3D modules, with also prefabricated HVAC. Bring it on site as a 2D element or a 3D room cell, pre-installed, prefabricated. This is 18-meter length. And then, at the end, we have today this shitty workflow, though we have in the digital planning mostly 3D models and 2D files, 3D models for the BIM exchange, and from this we create or we get Excel files, PDFs, 2D like DVD, DXF, or whatever. Then sometimes an ISC. And from this shitty data, we generate our own new 3D model for the production. So we cannot use the 3D model from the digital planning. So that is, that's a shitty workflow today, and it is the challenge today to create a good workflow. And these are some examples how we can use it or do it from the digital construction to the digital design. So we have this concrete wall, and we want to bring on facade element. We measured the point cloud, use this, and then we applicate digital facade design done by Rhino and Grasshoppers. It's done by Edita. And at the end, we produce it and bring it directly on site and hang it in. These are 5-meter height elements, 3.5 in the width, prefabricated and hang in a very short time. So another one is the back way at the end, from the digital design to the digital construction, building or build or construct without paper. So this is an acoustic wall built with 8,500 wooden pieces. Each piece is the same, but the position and the rotation of each beam is different. So from this, we have parametric planning. We had also simulations, and we can play with light and shadow. And at the end, we have produced 3 walls. It is a collaboration with the ETH we have done. So that means we tested augmented reality and a feedback system. So we have the digital model, and we have a PlayStation console, and built this, and rebuilt this for our testing with the camera, and then the camera measure the element, bring back the information, and then the tool or the 3D model say you have to rotate it or you have to move it a little bit. And at the end, if it all is right, you get a green borderline on this TV, and then you can press a button on the PlayStation console, and then it fixes at the end the actual position of the beam. So that is it's like a feedback system. If you cannot place this piece in the way that is given from the 3D model, so at the end you have both positions. That is the planned position from the 3D model, and at the end the real position of this wooden piece, and that is quite cool. I guess that you get the feedback and you can save this feedback directly in the 3D model. So that is part of the R&D with the ETH. And this is the finished wall. It looks very crazy and it works really, and you feel really, it's a good feeling if you stay in the room. It's amazing. The other one is from the digital design directly into the digital fabrication. So this is the future tree built with Basler Hoffmann and also the ETH. And what you see, I hope you can see it, is the wall of this position of the beam. So you have the right edge and the left edge, and the right edge is fixed on an existing building, and the left edge is hanging out of this, and you see that the beams are differently, the position of the beams are different a little bit, and this comes from the statical dimension. So if you move the point on the left side, the whole system reacts to the new position of this edge and reposition the beams at the end. So it's linked. The architecture model is linked to a dimensioning of the beams. And in this, at the end, we generate also the connectors parametrically with the statical tool. So we bring out, it's an export from the Rhino model directly in the statical software, and get back all the positions of the screws and the angles of the screws and the length of the screws. So at the end, we have all the information we need for the robot to drill the hole for these screws. Also, what we can do is a simulation. Can we produce these elements? The whole tree is cut in 5 elements, so that we produce 5 elements, prefabricate these elements and bring it on site. So the robot does all the cuttings and millings and drillings and place at the end these parts, and the quality check is done by the carpenter. He drill in also the screws that he can react to some tolerances by building these elements. And the tolerances is not coming from the robot. The tolerances is coming from the element. At the end, if you raise up the prefabrication of this element, you have more tolerances. You go in the height, and the higher you are, the tolerances are also higher, and they have to react to this. The position of this beam from the robot is exactly there as the planning. So, and these are the prefabricated elements. It's a double curved surface. Installed it like this. Transport it to the site, and then combine it at the end to a big tree, and also place it on a 3D printed column in concrete done by the ETH. And this is the whole tree, the column, and in the back you see one of these 3 acoustic walls done with the augmented reality. So, and this is now at the end, or how can I say, something about digital planning, that we bring in the model like in a parametric way into our system, and then I am in at the end. Now I can give the word to Edita, and they want, she will talk about I hope so, CoDeFa and whatever also, or what is the big challenge behind the new process or processes, or thinking about new processes between the collaboration of architects and companies.
Thank you, Thomas. Maybe now I can take over. Collaborative design of prefabricated facade systems, or CoDeFa, is a joint research project between ERNE AG Holzbau and HGK, Institute Integrative Design in Basel. We decided to do it after our experience with Lärmschutzwand, the project that Thomas showed you in his presentation. The focus of this research are non-standard prefabricated wooden facade elements. Historically, facades were the most prominent elements of the building, a favorite architectural canvas for architects. I think that at Timmerman is still this way. It was the part of the building most investigated and most invested with aesthetical, political, and cultural expectations. However, most of the facades of the buildings currently built are using individual industrialized repetitive solutions, and this, especially when you go outside of the big cities like Basel or Zurich, you see it in this in Laufenburg, in Stein, or in other places all around the world. They impoverishes the visual attractiveness of the buildings and also the quality of human interactions within them. And we can look at this problem from various perspectives, but in this presentation, I will focus only on two. So the construction industry is struggling with producing non-standard components. As far as the standard elements such as the walls and the ceilings are already being produced with a robot or automatically, especially at companies so digitalized like ERNE, the special elements like facades that require some adjustment rely on the manual production. And this is the costly process that limits the variations of the design possibilities. Architects, on the other hand, are usually uninformed about the manufacturing capabilities of the industrial partner. And that leads them to either overestimate or underestimate the actual possibilities and rather focus on the form and not necessarily thinking of how it's going to be produced. So it causes either higher production costs or inclination towards the standard solution to avoid possible risks. That is why in our research, our main research question was, how can we strengthen the communication between architects and the construction industry to bring more design freedom in the prefabricated? As a starting point of our research, we analyzed the current design and production process. We realized that in order to bring the innovation in the building sector, we need to work across disciplinary borders where most of the inefficiencies and miscommunication happen. As I and also my project team, Daniel and Maria, are specialized in new technologies, we decided to bridge the gap between architecture and engineering using this, and also between architecture and construction using this digital design and construction tools and also automated fabrication. As well as the early interdisciplinary dialogue, a method in which architect, engineer, and manufacturer start collaboration on the early stage of the design. We call it a collaborative design approach, and its goal is to bring better understanding of each other's priorities and to work together on finding the best solution to the given limitations in the design process. To meet these goals, we focus in three areas. We are developing the digital design tools for architects to design and rationalize, and for engineers to prepare files for the automated assembly. We are setting up a collaborative approach and fluent communication between architects, woodwork engineers, enhanced by academic researchers. And also we are reworking the existing processes and also develop the new ones to maximize the number of automated tasks and also that enable to expand the possible design space. The outcome is the process to design and fabricate unique facade systems. The first step in our research was to understand what in fact architects expect towards facade systems in terms of aesthetics, methods of fabrication, also collaboration with the manufacturer. That is why we started our project with workshops with architects. We invited 11 Swiss architectural offices, among which was also FHNW, represented by Magnus and Dominic, which was represented by 15 architects. Each of this office had various sizes and ways of work with the facades and architecture and tools. We gave them the task to design new facades on the existing modular buildings. We asked them to play with new tools, new ways of collaboration, new aesthetics, and also new thinking. And within just a couple of hours of this workshop, each of 7 teams came up with a unique solution of individualized yet standardized facade system and informed their design with the possibilities of robotic fabrication of ERNE. We used this workshop to guide our further research steps. So alongside this workshop, we also sent out the questionnaire to architects, where we asked them what is their desired design space. And it appeared that the most interesting facades for the architects are wooden beam or plate-based facades with a sophisticated geometry, surface, or assembly method. As far as the method of collaboration with manufacturer is concerned, architects expressed a desire to start collaboration on the early stage of the design. That is why we decided to start each new project with a collaborative workshop where architects' expectations are enhanced, if needed, with custom parametric design tools and confronted with the production possibilities and structural knowledge of our industrial partner. And lastly, for the form of the digital design tool, each architectural office has different experience with working with digital design tools. And also architects, as you know, like to keep their freedom in how they design. That is why we did not want to create a one-button magic solution, but rather we wanted to have some scripts that would help to enable architects to explore their design potential if needed. That is why we decided to propose a 2-step tool, which would be used by the skilled ERNE staff, where one would be a conceptual design tool and the other one would prepare the design for the robotic production. In parallel, we also observed the existing ERNE robotic fabrication process of the facade element, which back then was based on the manual production process. So all of the beams are assembled from the back, all of the facades, because for ERNE, it's very important that the screws are not visible from the front. So they are building the special template on which the robot was placing the beams, and then it was placing the substructure and screwing it from behind. This method is only applicable to the facades that are regular in depth and width, and rather restrict the design potential or design variations for the architect. That is why we realized that our main area of focus in this research should be assembly and not necessarily the geometrical manipulation of the elements. And to allow for the larger freedom, we proposed 2 alternative facade assembly solutions that allowed for the screwing from behind. In the first solution, we had a robot that would position the beams in the correct place, and we had a custom CNC table that would screw them from behind. In the next solution, we had 2 robot collaboration where one would place the beams from the front and the other one would screw them from behind. Due to the cost, together with the industrial partner, we decided to proceed with the robotic screwing and placing, as the robot is more or less 10 times cheaper than the custom CNC device. In the next step, we worked closely with our industrial partner. So we brought our knowledge from the FHNW, the design and parametric know-how, and we combined it with the technical know-how of not only engineers, but also of the craftsmen, people who are building this facade, to learn from them. We brought our small robotic unit, the KR6 that you can see on the left, and we set up a 2-robot collaboration. And we also worked with our partner in a close collaboration. So we were testing and also like proposing some solutions and testing them at the same time. And this appeared to be very, very efficient. In the next step, we were implementing our findings. So as initially mentioned, in our research, we developed continuously the digital and physical tools and processes to create a continuous design to production methodology. We created a digital toolbox, the prototypical tools that allow for the playful explorations of the possible design variations. And we use these tools as a base during the workshop, but this is not a necessary step in our research. So in fact, we wanted to provide for architects as much freedom as possible. And many offices like Herzog & Demeron have their own digital design, digital technology group. I know that you are called right now in a different way. like people who can really build for you the tools. But 99% of the offices normally appreciate this kind of support, but this is not necessary. Like what is important is that we are then supporting the architects with various knowledge, with the digital design knowledge, but also with the engineering knowledge and also with the manufacturing knowledge. In the next step, we are taking the geometry, which was created somehow, either with the digital design tools, but also could be generated manually. And we created tools using KUKA PRC in Grasshopper to translate this facade geometry into a set of commands for robots. These highly flexible tools are based on the geometry and allow for a wide variety of possibilities how we can process them. We can cut them on the table, so we can mill with the milling spindle, work with various end effectors, depending on the design of the facade. In parallel, in the physical space, we constructed our own tools that would allow for the mentioned before actions. We either use existing tools, such as this vacuum gripper that you can see over here, or we build our own tools that are like, for example, this asymmetric gripper that can hold and grab the beams of various sizes and depths. Or we also had the traditional tools like this screwing device that we connected to the robot or the table saw. In this project, we work in a very experimental and playful way, in a way how craftsmanship were working. So thanks to that, we managed to create a wide variety of design options for architects, both in digital as well in the physical space. The fabrication is based on the two-robot collaboration, where KR240, this is the big robot that you see on the left, is picking, positioning, and performing variety of operations on the beams, such as the cutting on the table saw, placing beams on the facade, cutting the beams with the saw on the spindle, and milling. And the small one is screwing the beams to the substructure from behind. For this collaboration, we also had to set up two robot exchange, which is based on the input-output symbol. When one is positioning the beam, the other one is waiting for the signal go, and then the other one is stopping, and the small robot is screwing. After it's done, it's sending the go signal to the big robot. So we never have clashes between the two robots. Within this project, we work with a variety of tools. We work with the available equipment, such as the milling spindle and circular saw on the spindle. We also adapted tools that are normally used in the manual production, such as the standard table saw, vacuum gripper, which we connected to the robot with a custom 3D printed adapter, screw gun, which we connected to the small robot. All these tools were activated through the robotic outputs. We also constructed our own equipment, such as this asymmetric gripper that allows to grab the beams of various sizes and place them in a close position to the other beams. We also built the assembly frame, custom log disposer, and tool changing stations. Thanks to this approach and cross-disciplinary craftsman work, we expanded the available design space and could work with designs that would be otherwise impossible to achieve. We managed to create a wide variety of design options for architects, both in the digital and also in the physical space. In the last couple of months, through these playful explorations, we built an impressive portfolio of various facade options. In these facades, we have explored various potentials. We played with the uneven distances between the beams, different widths of the beams, non-repetitive pattern of the logs. This is when we introduced the table saw, different depths of the logs, different orientations of the logs, non-repetitive division along the logs. All of the actions that I just mentioned, but on one facade, so non-repetitive width, length, and depth of the logs. Plate-based facade, this is when we started to work with the vacuum gripper, shingle facades with pattern, multi-layered facade with 2 or with 3 layers, structural facade with milled joints, pattern milled on the facades, and also pattern milled on the facade along the wood grain. We were exploring the design potentials of the newly developed tools, and then each of them was evaluated by engineers and also the carpenters, if they are economical, sustainable, and also if they are okay in terms of performance. And some didn't pass this test. For example, the structural facade with milled joints would allow the water to flow in between the milled joints and the second beam, and then the wood would rot. So we had to somehow reject it. And also this facade with pattern milled of the facade opened the grain of the wood and could not be used outside. For our final demonstrator, we wanted to choose the systems that present the wide scope of our design and fabrication possibilities. That is why, in the end, we decided to work with these three options. The demonstrator are four full-scale facades that we applied on the existing modular building. We constructed them within the last 3 months of our research. The base was the simple modular building that is standing in Stein in front of our headquarters. Our architectural concept was to create a frame from the front and the back facade, which represent the beam-based systems. And two side facades were embraced by this frame and created a dialogue with it. The last facade was mounted only last week. This is how it looks like from the back. Within the systems, we also chosen the systems because they show the three main traditional facade systems that can be observed in the traditional wood construction in Switzerland. These are the shingles, beam-based facades, and so-called board-on-board facade or Bodendeckel facades in German. With the help of this new design and production technologies, we expanded its aesthetical expression and tried to keep the original logic and performance. What was also important for us is to show with this demonstrator the maximum of our constructed possibilities of our new fabrication toolbox. Each of these facades had different construction logic and also challenges. We started the production with the shingle facade as it was the simplest. Here, the most important was the efficiency of the production. That is why we decided to mount the substructure manually, because it was always in the same distances towards each other. Then each of the elements was picked by the robot with the vacuum gripper from the log dispensers, and then cut on the table saw from two sides. Then it was positioned by the big robot on the frame and screwed in 4 points by the small robot. Thanks to this approach, we managed to optimize this process pretty much. It took only 1 minute and 10 seconds per element, per one shingle, which was 3 times shorter than we expected. And that means that also the price of this element was significantly reduced with this time optimization. In the beam-based facade, we had a completely different approach and different system. We work with the long linear elements that had very, very thin sections. And here, the main priority was the accuracy of the production. We worked with the asymmetric gripper. We had 10 different disposers for 10 different beam types. Each of the beam was cut from one side only on the table saw. And then while assembly, the gripper was sliding and holding the beam in the correct place. We also had to make sure that the screw device was screwing exactly in the middle of these very, very thin beams. As a result, we managed to get to the accuracy of the manual production, which is the difference in the length between the beams was within 1 to 1.5 millimeter margin, which is comparable to the manual production. And lastly, we worked with the mixed facade. It had a complex production system which combined both grippers, a symmetric gripper and vacuum gripper, while most of the geometrical manipulation on the individual beams was done manually before the fabrication. We started to work with the vacuum gripper, where the first 2 layers were assembled with the vacuum gripper. And then the second layer was cut from one side on the table saw. Then it was screwed to the substructure from behind. And we changed to the symmetric gripper that picked the beams. Each of this, we had 3 types of the beams, and they were different with they had different dimensions and also different angle from the back. In the end, that was the most efficient facade, even though it was the most complex, because we managed to build 1 panel in 35 minutes. So in the end, that was the cheapest facade. What I also wanted to say is that within this process, we also wanted to learn if this kind of facade, this kind of mixing of different tools can be also applicable in the industrial processes. So we wanted to optimize the processes as much as possible to see if ERNE can really offer it to the architectural partners on the for the reasonable price. And these are the four facades that we built: the shingles, the beam-based facade in the back and the front, and the Bodendeckel facade on the side. You see the close-ups of this facade on the right side, and then this idea of the frame that was embracing the two-side facades on the left. It is important to say that these mock-ups do not exhaust the design potential of the proposed system. They open the possible paths for the future exploration of architects, as the goal of this research is not to create a catalog of available options, but rather to give architects the process to design unique facade solutions in a collaborative way with the industrial partner. Using exactly the same design tools and exactly the same fabrication methods, we could create such a variety of options for the shingle facade, for the beam-based facades, or for the mixed facade. The project is was officially finished at the end of November. And we already started to collaborate with one architectural office from Basel, SS Architekten. We are working on the application of our research on two facades of the residential building, which will be constructed in 2021-2022. We already had a series of workshops where we tested the developed processes and tools, and we improved them further. ERNE also decided just today, Thomas gave the green light, to buy the bigger robotic unit on the linear axis. And this bigger robotic unit would allow to build much bigger panels that will be 4 meters by 2.8 meters. And that means that these panels will be even cheaper and even faster to construct. We are also planning to improve digital design tool and expand creative freedom of architects. As the current system requires the presence of computational designer, it will be perceived as a limitation for architects. That is why we are thinking of the way how we can change it into the more intuitive tools that will be based on the learning algorithms, in which digital tool can be a sort of a design partner for architects.
To complete this presentation, we just, ERNE is a company that Wood Solutions is familiar with. We've run tours through the plant in Switzerland 2 or 3 times beforehand, and they must be, been around the world. They must be one of the most advanced companies in this area. So this is very good for them to allow us to share their time to say what they're up to. And admittedly, I've never been there, has been blown away at what they're up to. So just completing this webinar, just to remind you about the CPD questions. Again, if you had how many axes of movement, if you said 5, you'll be right. What function did the augmented reality provide in building acoustic wall panels? That was for positioning. And name 2 of the many functions robot played in the fabrication of the timber facade. There was like about a dozen things, but it screwed, which was new to me, and cut and held and all that type of things. So that was the type of the answers we're looking for. Just to wrap up, so just a reminder, this presentation will go on to the Wood Solutions webinar thing. We'll use the original presentation. Apologies for some of the quality. It was optimized for the thing for Zoom, and it wasn't the best solution, so I converted it out back, and it did improve the quality. So we'll have that presentation up there for you. Remember that we'll send out the certificate to you, and the CPD for your CPD questions. Please keep that in a safe place. And also, in the part of the CPD question form that we send out, we will also have an opportunity for you to fill in a survey, which will be the back of the form. Please, could you take your time and do that, because it's our way of knowing what you want to see and hear. And just to now to go on to the next webinar, it will be on Tuesday. Webinar will be on the 13th of April. And it will be on how we can build Australian future 7-star homes for Dr. Christopher. And so it'll be very interesting to see how that presentation. So at that point in time, I now wrap it up because it's now noon, and see you at the next presentation. And also I wish you a happy Easter for the Easter break. Thank you again for your time.